Hello, welcome back. This is more stuff on graph theory. In particular, we're going to start looking at trees. So let's take a look. So 10.4, trees. Hopefully my microphone is on. Let me make sure it is before I spend a half hour recording something. Hello, is my mic? Yeah, it's on. Okay. All right, so let me go back to this. Sorry about that. Thank you. And okay. So, definition, what is this thing? It is kind of what you think it is. You've dealt with trees before. For example, the most common example clearly is like a family tree, right? So you have some parents, and then they give birth to some offsprings, and then those people give birth to more people, etc. Okay. Um, right. So in particular, we want you know a more complicated definition, I guess. A graph is a tree if and only if it's connected and it's circuit free. So the graph is connected. In other words, there exists a walk from any vertex u to any other vertex v, and it's circuit free. Okay. So there's no, I guess you could say, like a loop. Let me give you some examples. Okay, so some examples. The trivial tree, which is just a vertex. Okay, that's a tree. The flux capacitor, which was made famous in the movie Back to the Future, is a tree. If you've not seen that, run out and run it. It's a little old though. So if you try to make the flux capacitor a little more complicated, it no longer becomes a tree, right? So if I add in another edge there, now it has it has a circuit, so it's not a tree. Okay. Likewise, if you try to augment the flux capacitor by simultaneously adding in another flux capacitor, so maybe Rick from Rick and Morty would have done something like this. That's no longer a tree because it's not connected. Okay, so not a tree. Even though the components are trees, overall it's not a tree. Okay, so some neat examples. Some actual working examples from real life. Some applications, I guess, probably a better title for this section. 10.4.2, we have a decision tree. Okay, and I've actually wrote one of these for our classes here at Tri-C, where we give people tests and then look at their score, and then based off their score, we place them in classes. Okay, and just doing it with a decision tree gets rid of all of the human issues, like, oh, I'm going to let this person take this class just because they look cool or something like that. I don't know. So, for instance, if you have a test, maybe it has a score 1 to 20, and we're going to say if you get over it, if you get whoops, so I need to adjust these inequality symbols. Let's say if you get over a 10, then you could take math 220 or something, MTH maybe. Sorry, and then I just screwed it up again. If you get less than or equal to 10, then you have to take math 210 or something. I don't know. Or maybe they send you to math 101. You got to retake that. Okay. Other examples, 10.4.4. Back when I was in college, they were working a lot with molecules and graph theory. In this book, they talk about this example of saturated, I think it's saturated hydrocarbons, and Cayley studied these things and was able to prove that all these hydrocarbon things were actually trees. So they don't actually have any circuits in them, just based off of the chemical bonds of these things. So hydrocarbons will be carbons and hydrogens, and the nature of these kind of forces them to be trees. Okay, so you study these diagrams with graph theory, and you can make some cool observations. Okay. And then for the rest of this section, there's just a bunch of theorems, and you use these to kind of answer questions, randomly generated questions from WebAssign. There's like one proof in WebAssign, but I'll go over the proof here in a second. Okay, so the book's just going to call these things characteristics of trees. And the first kind of characteristic, I guess, call it part A, lemma 10.4.1. So lemma, I always think of it as kind of a little theorem that's used to prove a bigger theorem. In our book, this lemma says any tree with that's not trivial, so any tree that with more than one vertex has at least one vertex of degree 1. I don't want to go through a lot of the proof stuff. I'm not all that great at memorizing proofs, but I think this proof is awesome because it kind of has it's an algorithm, so you computer science people really appreciate it, and it works as a proof. So some of you, if you're more of a math enthusiast, you're going to say, "Oh, this is baloney. You can't. It's not worth, you know." Well, a lot of proofs these days are kind of I wouldn't say a lot, but some of them, like the four-color theorem, if you know what that is, was proved using a computer, where they just went through, I think they went through like case by case. Like they could prove a lot of the cases were true, but then they later had to go through the harder ones with computers. And the problem with using a computer to do a proof is sometimes you don't understand, especially if the computer is doing like a machine intelligence type thing where it's just kind of going rogue and figuring it out on its own. It's kind of hard to understand how the computer figured out the proof. So that's a cool field of study. If you're wondering why we spend so much time on proofs, what does this have to do with computers? In my opinion, thinking is, computers. That's where it's at. Thinking, doing proofs is really, part of it. So anyways, let's take a look at this thing. Hope you like it. We'll just let T be a tree. So let T be a particularly but arbitrarily chosen tree that's non-trivial, so with more than one vertex. And then we're going to sort of build this algorithm. So consider the following procedure, or if you'd rather, algorithm. Okay, so step 1, let's just number them. I'm not going to put step 1, step 2, that's a bit silly. Okay, so first, as soon as my pen works, we'll do this. First, pick a vertex V, pick a vertex from the graph T, V, and an edge that's incident on V. Okay. Okay. There's more than one vertex, so it has to have an edge. Okay, so this has to be doable. It's also connected. Okay, so you're not going to end up on a vertex that's just out in the middle of nowhere and doesn't have any incident edges. Okay, so once we get this, we're going to sort of go into the program. So 2, we'll say while the degree of this vertex that we've chosen, which we're calling v, while the degree is greater than 1, because if the degree is equal to 1, we're kind of done, because that's what we're trying to prove. We're trying to prove that there's at least one vertex of degree 1. So supposing the degree of this vertex we're sitting on is greater than 1, we're going to repeat the next 3 steps. Okay, 3, 4, 5. Okay, so step 3, let me indent. I hope I'm not abusing computer scientist notation or something. But anyway, step 3, we'll choose this other edge, E prime, because the vertex V has degree more than 1. If it didn't, we would be done. If we got lucky enough to pick a vertex and its degree was 1, we would be done. So what we do is choose a different edge. So E prime, which does not equal E, that is incident on this V vertex. Okay, so you can draw a picture, and that doesn't hurt. I'm not big on drawing pictures because sometimes, but here's the vertex in this crazy graph we've kind of populated, and there's, I don't know, it has to be a tree of some sort, so there's no circuits. Okay, so let's say we call this V, and there is an edge that's incident on V, so we're saying that maybe this was E, and what we're doing here is saying, okay, the degree of V was greater than 1, so let's pick an edge other than this edge that we started with. Okay, so we'll call that one E prime, so maybe that's this guy over here. Okay, so when I say pick up in the step 1 here, pick a vertex V and an edge, maybe I should say call that E. Okay, an edge E that is incident on V. Okay, so this is the edge E that I'm starting with, and this is the edge V that or the vertex V I'm starting with. So while the degree is greater than 1, choose a different edge incident on V. Okay, and call that E prime. Okay, so 4, then let V prime be the vertex on the other side of E prime. So we'll say this is V prime up here on the picture to the left. Okay, so let V prime be the vertex on the other end of E prime. And then in the last step, all we're going to do is rename. Okay, so let V be now V prime, and E be E prime. So on my picture, which is getting overly populated, I'm going to now get rid of this as V and call it V, or sorry, get rid of it as V prime and call it V. Okay, so this is no longer V. And I'm going to get rid of E prime and call that E. Okay, and then you just continue it, right? So if the degree is greater than 1, then you pick an edge incident on V that's not E. So then you would call this, still working on the graph to the left, call this edge E prime. Okay, and then you call the guy on the other end of it V prime. And then you get rid of this, and you call V prime V. So you get rid of that, and then call E prime E. And at this point in my graph, that has degree 1. Okay, so then I'm done, and that would be the degree that I needed to find. Okay, so a cool kind of computer type proof that we don't always see. I hope you enjoyed that. Okay, so the world is the limit when you're doing proofs. Okay, don't be constrained. This book does go out of its way to kind of try to make all proofs templatable. But once you get into the graph theory stuff, you're kind of starting to see, well, these proofs aren't written like that. They're not. I mean, they'll try to make them like they're fill in the blanks, but they're not really fill in the blank proofs anymore. And this is really where it gets very creative, and you can make up your own proofs And then something like this, maybe people would argue a lot about. But really, it's really, really interesting stuff. And don't feel like you have to do it this particular way. Some people just draw pictures and try to pass that off as their proofs. And I think that's okay too. Maybe your professor or colleagues will argue, but that's part of math. Okay, you guys argue. Okay. So, anyways, the algorithm well, it's circuit free. So you might argue, well, wait, what if I circle around in my graph and I come back? Well, note the graph T is circuit free. So you're not ever going to really loop back onto the same vertex and then get caught in an infinite loop. Okay, so there's no loops. And then also, it's not going to go on forever because the graphs we're dealing with have a finite number of vertices. So it's got to terminate. The algorithm will terminate or halt. Because there's a finite number of vertices. Okay, so anyways, there's that. I think in the homework they'll actually look at maybe one or two problems that have infinite vertices, and those are weird. I won't put those on the test, I promise. But anyways, some definitions now. So that was part A. Part B, some extra definitions. First we have a terminal vertex, which is sometimes called a leaf. This is a vertex that has degree equal to 1. So the degree of the vertex is equal to 1. But the trivial tree is also, it's just having a single vertex. That's considered a terminal vertex as well. Okay. So I guess you could say degree of v is 1 or 0. But if it's degree 0, that'll be the only vertex in the tree. Anyways, internal vertices. In later sections, we characterize rooted trees in terms of their terminal vertices and internal vertices. But internal vertex is, if we scroll back up in my notes, and in the flux capacitor, the vertices at the edges, so to speak, are the leaves. So the ones I just circled in blue are leaves. And then the internal vertex, there's only one. That's the one on the inside. Okay, so an internal vertex is a vertex with degree greater than 1. And then we just have a whole bunch of more theorems. So four more theorems, so please bear with me. I'll prove the last theorem. You want to have these theorems kind of internalized for some of the questions. As you go through the homework, you may want to mark down which theorem you really need to have for the test, for the final. For any positive integer n, any tree with n vertices has n minus 1 edges. The proof in the book on this one's really cool if you read it. It's by induction. Okay, I'm not going to go through it. Lemma 10.4.3. Okay. If G is connected, and you have the circuit C inside of G, you can remove any one of the edges of C and G will still be connected. Okay, the proof is kind of nasty in the book. I'll just sort of clue you into how it's going to work. You can imagine here's a graph that's connected. Okay. A connected graph means that from any point there's a walk that will get you to any other point V. So let's say this is U and this is V. Let's label these A, B, C, D, E, F. So what the theorem is saying is that you could basically get rid of one of these segments and it will still be connected. And it's kind of, if you think of like maybe a loop of string, you can cut the loop and it'll still be a piece of string, it'll still be connected. So in this case, if the original path or original walk was U, A, B, C, D, V, now instead we could kind of just loop around the other direction. So we could go U, A, B, uh-oh, that's not there. So we can go backwards, A, and you could repeat vertices and edges whenever you're doing a walk. So that's pretty much anything goes. So B, A, E, F, D, and then you could still even go back and hit C, and then D, and then V. Okay, so it's not a big deal. It's really kind of nasty and tedious to have to prove it. Okay, so we're going to kind of skip that one and leave that to you for the reading, rather than forcing me to memorize it and do it here for you. Theorem 10.4.4 then says for any positive integer n, if G is connected graph with n vertices and n minus 1 edges, then G has to be a tree. Okay. Okay, so this is kind of goes along with the previous theorem on trees. So for any positive integer n, if G is connected with n vertices and n minus 1 edges, then G is a tree. Okay, so I believe our previous theorem says, given that it's a tree, right, for any positive integer n, any tree with n vertices has n minus 1 edges. So you're kind of starting with a tree, and then you're able to say if it has n vertices, it has n minus 1 edges. Here, if you have a connected graph with n vertices and the n minus 1 edges, then you could conclude it's a tree. So it's kind of trying to go in the other direction, but you can't quite make it there. Okay, so maybe interesting to compare and contrast those two definitions if you get a chance. The last sort of theorem here is just a corollary from these other theorems, so 10.4.5, and I will go through this proof. If G is any graph with n vertices and m edges, and the number of edges exceeds the number of vertices, is greater than or equal to the number of vertices, then G will be forced to have a circuit. Okay. So one trouble with these proofs is the notation is a little nasty. So one thing I would like to do is kind of introduce this notation. I may have used it before, I don't remember, but if not, I'll notate it here. This means the number of vertices in the graph of G. Okay. Okay. What else do I need? I think that's all I need. No, sorry. This thing is the number of edges in the graph G. I think there's a mistake in the book. It says note mistake. It has this n whoops, n sub I minus 1 like this. It should be n sub I minus 1 like that. So it's not in the subscript. It's supposed to be out of it. Okay, so anyways, let's try to go through the proof here. And it's a proof by contradiction. So instead of supposing that G has a circuit, we'll suppose that G doesn't have a circuit. Okay, so we'll start with the same suppositions. Suppose G is any particular but arbitrarily chosen graph with n vertices and m edges. N is, or rather m is greater than or equal to n, and we'll say that G is not connected, or G does not have a circuit. Okay, so what we're going to do first is kind of consider all the components of G. So we don't know if it has components, but we'll suppose it does have some components. You know, maybe it just has one component, maybe it has k components, but we can look at all those components. Okay, so let G1, G2, all the way up to G sub k be the connected components of the main graph G. Okay, we want to note how many vertices each of these connected components has. So we'll say the number of vertices of a particular component, G sub I, so it will be called little n sub I. Okay, so then we'll note that the number of vertices on the actual graph is equal to the sum of the number of vertices on all these connected components. Okay, so the number of vertices on each particular connected component is just n sub I. Okay, and then the total number of vertices is given back here in the beginning of our supposition, right? So the number of vertices on G is n. So the number of vertices from the connected components will add up to equal the number of vertices on the overall graph, which is n. Okay, so you can maybe even draw a little picture to try to help you out. So let's say we have a bunch of little connected components over here. Okay, so the number of vertices on the one completely to the left is 2, and then the number of vertices on the one on the bottom is 3, the number of vertices on the one on the top, 1, 2, 3, 4, 5 is 5. The total number of vertices, all you have to do for this graph, so this entire thing would be considered like G. Okay, and then this maybe is G1, and then this is G2, and then this is G3. The total number of vertices is just the sum of the vertices from each of the components. So the number of vertices on G would be equal to 2 plus 3 plus 5, which is 10. Okay, which is all this symbol stuff is saying. Okay, so next, note that each of the components of G are basically trees. Okay, because we've supposed that G doesn't have any circuits. So if G doesn't have any circuits, then certainly all the little bits and pieces don't have circuits, right? So G1, G2, and G3, they're not going to have circuits either. Okay, so G doesn't have any circuits, and then on top of that, what else? Well, each component, because it's a tree, then we can say, and they're all connected. Okay, so these are all connected components. Doesn't have any circuits, and each GI is connected. So that means each GI is a tree. So if each GI is a tree, we know the number of edges on each G sub I. Okay, so note each component of G is a tree. Thus, the number of edges, which I can write n of E of G sub I, will equal just n sub I, the number of vertices on each edge, the number of vertices on each component, then minus 1, right? And that's where that mistake is in the book. Okay, so now I can do this comparison. So now I can say, well, let's think about the number of edges on G, the whole graph, right? The number of edges on G should equal the number of edges from each of the components. So if you look back at that graph to find the number of edges on G, just add up, 1, 2, 3, 4, 5, 6, 7. There's 7 edges on G. Okay? So we could write that out in our notation now. We're given in our supposition that the number of edges originally is little m. Okay, so little m. That's the number of edges on G. So we'll say little m equals the sum. Let's not even go there just yet. We could just say little m is equal to the number of edges on G. And to get the number of edges on G, all we have to do is sum up the number of edges on each of the little subgraphs, the G sub i's. And we know how many edges are on each G sub I. That's just the n sub I minus 1. Okay? And we're summing this up over each component. So it's going from 1 to k. If you look back, there were k components. Okay? So if you look there in green, I'll mark it in green, there's k of them. Okay, okay, so what we have here is a sum of a finite sum, so we can separate that thing. We could say that's the same as the sum of these n sub i's minus the sum of 1. And again, it's going from I equals 1 to k. I equals 1 to k. That first term is just the sum of the number of vertices on all the little components. Okay, and we said that the number of the sum of the vertices on the components equals the number of vertices on the overall graph, which was n. Okay, and then minus this other sum, which we have formulas for, that's just k, right? If you have k things and you're adding them up, so remember, if you have the sum from I equals 1 to 5 of 1, it's just 1 plus 1 plus 1 5 times. So the answer is just 5, right? So the answer to the sum from I equals 1 to k of 1 is just k. Okay? All right, so we've assumed that there has to be at least one component. So what we're trying to figure out what this k value is, right? What can k be? K is the number of components we have, and in the worst case scenario, k is greater than or equal to 1. Maybe it has one component, maybe it has 2, maybe 3. Okay, but regardless then, if k is greater than or equal to 1, this n minus k must be less than n, because you're taking n and you're subtracting away something. Okay, so what? Well, if you look at the beginning and end of this chain of expressions, it implies this implies that m is actually less than n, which is a contradiction. If you look back in our initial supposition, we said what? We said m is greater than or equal to n. Okay? We supposed m was greater than or equal to n. So this is a contradiction, and therefore we must have a circuit. Okay, so that's the end of the proof. The other problems are just kind of, they'll give you maybe some facts about a graph. Let's maybe look at one of those. So they'll want you to explain it, that it doesn't exist, or find a version of it. So for example, number 8, does it exist? And if it exists, then draw it. Okay, so let's say there's a tree with 9 vertices and 9 edges. Does that tree exist? So you kind of have to go back to your theorems and scroll through and see if anything fits. Yeah, so C, for any positive integer n, any tree with n vertices has n minus 1 edges. So if I have 9 vertices for a tree, you have to have 8 edges. So there's no way to have this happen. Okay, so this is can't do. Be a little careful. Sometimes they're not exactly just asking for a tree. They want a graph. Okay, so here in number 9, they want you to do a graph that's circuit free. Has 9 vertices and 6 edges. Okay, so if you tried to do a tree, you would be in trouble, right? Because you would have to have 8 edges, but you could pull this off. Because you can make a graph that's circuit free and disconnected. That will do the job. So let's just kind of, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and I think that'll do it. So no circuits, so no loops. 6 edges, 1, 2, 3, 4, 5, 6. Whoops, went a little too far. 6 edges, and then supposedly 9 vertices. So I need 1, 2, 3, 4, 5, 6, 7, 8, and then you can just put a random one out there, 9. Okay. Okay, so be careful about that. Oh, that's it. I think we're done with this section, and I'll see you next time. Okay. Okay.